Okay, this video discusses how to capture transient responses. So we're going to be looking at both open loop and closed loop systems here. And what we want to do is be able to capture how the plant or the system responds to a step response. Now, a step response means that the input or the set point is at one value and goes directly to another value. So you make a change. The most common is what we call a unit step response, which starts at 0. So the system we're putting nothing into the system, so the system is basically at rest. And then we go to 1 unit. So we put in a 1, whether that's 1 volt or 1 meter per second or whatever, depending on the type of system, what the units might be. But we make a step change, so it goes from 0 immediately to this non-zero value. And then we want to see how the plant or the system responds to that change. So we're going to do that with an open loop system, and then we'll do it we'll look at the closed loop system. But the point of this video is more to look at how do you set up a digital oscilloscope to capture this. So let's take a look here. Alright, so I have an oscilloscope here. The oscilloscope that I'll be using for this is the Tektronix TBS 1052 digital oscilloscope. And it's a 2-channel. It's a pretty standard 2-channel. You have 2 input channels and then your time settings here. So we're going to go over running those. Now, most digital oscilloscopes will have a button like this one that says auto set, and if you're using the scope to capture a normal a regular repeating sine wave or square wave or something like that, the auto set button works great. But for this application, you do not want to press the auto set. Okay, so you really have to go through and manually make these settings. So one of the first things we have to do, of course, is select our probe. So let me talk about the probe here. So when you get an oscilloscope, usually it'll come with an official probe here. It has like a coaxial type connection, and then there's usually a little kind of a pinch connector on here, so you can actually clip it onto a wire and capture it, capture the signal. And then there's a little alligator clip for ground. Okay. Now, most of these probes that come with scopes are what we call a 10 times attenuation probe. So what that means is that if the signal is coming in, it basically is going through a voltage divider inside of the probe, so that by the time it feeds it into the actual scope, you've reduced the signal by a factor of 10. Now, as long as your signal is strong, that's not a problem. But if your signal is kind of small to begin with and you're reducing it by another factor of 10, then you can get a lot of noise in there. So in that case, you want to use a 1 times probe. Now, this particular probe here, it actually has a switch on it. And if you read here, you probably can't see this in the video, but it actually says like 1 times here or 10 times. So depending on where you switch it, it'll be either a 1 times, which is just a direct feed to the scope, or a 10 times, which runs it through this voltage divider here. So whenever possible, I actually recommend that you use the 1 times, especially if your input signals are noisy. or small enough to be down into near the noise range, because that'll increase the amount of voltage actually getting to the scope. Now, if you're using really high voltages, like 50 volts or something like that, then you would definitely want to use the times 10 probe. Now, you may also have, sometimes we use some made up probes here, which just has a standard BNC connection with some alligator clips on it. So if you have a probe like this one is a 1 times, okay? So there's no 10 times. But the catch is that you need to make sure when you set this up, when set up the scope, that you have the scope on the correct setting to match the probe that you are using. So again, I'm gonna put this on the 1 times setting, and I'll be using the 1 times probe here. So what we do is we come over here and look at our oscilloscope. We see the channels. I already have the first channel connected, and so I'm just going to put this here on the second, and so there's my second setting. This third connection is for some sort of external trigger. We won't be needing that today, so I won't be using that connection. Okay. So our system is an RLC system. So we have this little system made up here where it actually has 2 different size resistors. We can flip a switch to switch either to a 1K resistor, which is obviously a lot of resistance compared to a 50 ohm resistance. And so what we're going to be looking at, our output is going to be the output across the capacitor. So it's a series inductor, capacitor, and resistive circuit. And so the input is going to come in here through this red line, which goes into one of the 2 resistors, depending on the setting of the switch. And then the other side of those resistors are attached to the coil. So again, it's a series connection, so it's going to go through the resistance, then through the coil or the inductor, and then to the capacitor. And then what we're going to do is we're going to be measuring the voltage across the capacitor. So that's going to be our output voltage. And I've got this connected up here to a standard compact logic PLC with some lights and switches already pre-wired to it. And what we're going to do, we have this terminal block here, so it's wired in. So we're going to use a analog voltage out. So we're coming out of pin 21 of the terminal block, which is channel 0 output of the analog output, and we're going to be feeding that in to the input of our RLC circuit. And then we're going to take the voltage of the capacitor is going to be what we're going to feed back into the PLC, which is going to be channel 0 of the PLC. So that's pin 15. And then the grounds of both of those channels are connected together. And then I have my oscilloscope. I'm going to attach the alligator clip groundings for my scope so that my scope inputs are both grounded. Okay, and then I'm going to use the clip piece here, and I'm going to just clip right on that wire. I actually left just a little bit of copper bare sticking out from the screw here, so that I got enough that I can just get this clip on here. And so I have my input to the RLC circuit. The RLC circuit, again, is my system that I want to look how this system responds. And the output of this system is the voltage over the capacitor. Okay, again, it's a series RLC circuit. All right, so to set up the oscilloscope, we're going to have to do several things. Number one, as I mentioned earlier, we don't want to press the auto set feature, and for trying to capture a transient wave that we're going to be doing auto set doesn't have enough information. So we have to go through and manually set them up. So the first thing we want to do is set up our voltage channels for our for both channels. And so we're going to start by setting the probe. So we're going to set our probe here, and okay. So let me just kind of go through here. What we're going to do is set our probe to make sure it matches our type of probe, and if it's a switched probe like I have, that we have the probe switched to the correct setting to match the setting on the oscilloscope. We're going to go to DC coupling. We're going to set our grounds, and we're going to set our voltage per division that we expect, and we can adjust these later and take another reading if we have to, but we want to at least try to get close to start with. And so I'll start with those, and we'll come back to the time settings. Okay, so you may not be able to read the actual scope values real good on the camera here, but I'll explain what they are. So if I press the 1 here, this gives me channel 1 settings, and the first thing is the coupling. So if I press this button, I get 3 choices for coupling. I have AC, DC, and ground. And so what I want to do is I can move this multi-purpose knob here to select what I want, and what I want is DC. So I want to make sure that that states DC, and then I press that and select it. So it says DC, and then it's going to down the 4th one down here says the probe. So the same thing, if I press the probe button, then it shows me some more options, and I want to set the attenuation to be ×1, because I'm going to be using ×1 attenuation. If you only have a ×10 probe, you need to make sure that that says 10 times. So you just need to make sure that it matches the probe that you have. Then we press the number 2 for channel 2 here, and we get the same thing. So we set the coupling. We want to make sure we set the coupling to DC, and then we want to set the probe attenuation to 1 times or 10 times, depending on what type of probe we're using. Okay, then I'll press this button. That'll just make that menu go away so I can see the full terminal. Once we've done that, we want to set the ground on here. So if you look, it's really hard to see, but there's a 1 and a 2 here. That is our ground reference. On the digital scopes, they just always show you that, which is kind of handy. And so to adjust that ground, what we do is we adjust the knob for that channel. Okay, and so as I raise that up or down, you can see this little tag on the left moving up and down. That tag is where ground or 0 volts is for that channel. And then we set that for the other one. And what we really usually want to do if you're doing a step response is get it at the very first dotted grid line above the bottom. So you never want anything right on the very bottom, because if it goes below that just a hair, you can't tell whether it went a lot or what. So you always want to be on a grid line. Okay, so we set those, and then we set our volts per division. Okay, depending on what you want your volts per division to be. I've got this, I just changed it to 1 volt per division for both channels. Okay, most of the time you want to try to compare the two, so you probably want to have them both set to the same. Okay, but you know, if you need to, you can adjust that as you're taking your traces. All right, but that sets up your channel to capture the voltages. So now let's look at our timing. Okay, so when we look at the timing, we want to go to the timing section and we want to set our time. So when you do that, you have to come in here and we'll set the actual time. If you don't know how fast the system is, you may have to adjust it again. But again, we'll do multiple tries and make adjustments as you need it. The next thing we'll do is adjust the trigger level. Since we just want to capture something that's just going to happen for a short amount of time, that's what transient means, right? It's just between two states, two steady states. Steady state means it's not changing. A transient means that we've moved from one state to the other, and that's what we want to try to capture, is what's happening when we're moving between these two states. So we need a trigger, all right? And so we'll set a trigger level, and the trigger level, you don't want it to be like right at 0, because if there's any noise in the system, you'll get a false trigger, and so you need to make sure you set that trigger ahead of time, or above the noise value. Once you set the trigger level, okay, then we will go into single mode, and when the voltage gets above that trigger, it will initiate the capture of that transient response. Okay, now to do that, most of these digital scopes will put the triggering right in the center of the scope. But if we do that, then we're only going to see half of it, because we're only going to capture stuff that happens after the trigger. So kind of like what we did with the voltage, we want to make sure that we shift that trigger to the first grid line on the left. It doesn't have to be 100% exactly on that, but we want it near that, because if we have to adjust our time, that trigger is going to shift on us. And so we want to get our time set at least close to what we want, and then adjust our trigger. So let's take a look at the scope here, and my time settings are over here on the right of it, okay, which is pretty common for most scopes. And so this is the time controls. And the first thing that we have here is well, maybe not the first thing. We have the trigger level. Okay, so as I adjust this adjusts the trigger level. Okay, if I adjust the horizontal, that actually shifts where it's at on the screen. So let me try to capture the whole screen and the controls here. So here you see this T. This T tag here indicates the trigger point. And so, as I said before, normally that trigger point, if you hit that auto set, it's going to put that way over here at the very center. But we're going to be capturing things that happen after that trigger point, so we want to, and then they're not repeating. So if we left it in the center, we'd only be able to see half of our usable screen. So we want to use as much screen as possible. So I'm going to set the trigger over here at this first grid point. I don't want it right on the line, but I want it on that grid point. Now, with most of these digital scopes, it doesn't have to be perfect, because we can shift it after we capture it, but we don't want it to be close to that, or it won't collect enough data. So we set it over there pretty close to that edge, and then what we're going to do is we're going to set our timing. All right, and again, we need to know how fast our system is, and so we may have to adjust this a couple of times if we're not really sure how fast the system's going to respond. And then when we perform closed loop control, we can speed the system up, so we may have to adjust it again. But we adjust our scaling. So my scaling here is currently at 500 milliseconds per division. So remember, the settings are per division. So each square on the scope screen here is half a second. So what that means is when I initiate this trigger, right, there's actually 10 blocks across this entire screen. And if it takes half a second to cross one block, right, and it's going to take something like 5 seconds to make it all the way across the entire screen. So when, you know, this system that I'm working with is not real fast, so it's going to take it, you know, 3, 4, 5 seconds or more to respond. And so we need to make sure that we have our time setting low enough that we can capture it. But when we trigger it, we're going to have to wait that 10 seconds for it to actually collect all the data in here. So it'll be a pause. We'll see that when I initiate it. Now there's a button here called the single, and when I press this single, it turns green, and it shows you down here at the top of the screen here, it says the word ready in like yellow. That tells you that it's waiting for the trigger. All right, and then if I trigger it, then so I'm going to switch. I'm going to hit this switch on the PLC that's going to send step response and going to initiate that, and it says triggered. So it turns green here and it says triggered, and then you can see the it took about 10 seconds, and now I have a response. Okay, this is what we call an underdamped response. It's bouncing around quite a bit, but eventually it's going to settle down. Now if you look at this, it's still bouncing around quite a bit here. So if I adjust my horizontal position, you see I ran out of data and it hasn't straightened out yet. So if you want to see it totally settle down, I'm going to have to change my horizontal time. So I'm going to change this down to 1 second, and you see how it kind of scrunched it together. Now I got to shift my trigger all the way back over here near the left, and then I'm going to press single again, and when I press single, it triggers. So it says triggered right there, but it takes like 10 seconds, or actually it's going to take, yeah, it's going to take 10 seconds for this, because I'm at 1 second per division. All right, but now you can see that the actual signal then has settled out to a pretty much a constant value. It's still bouncing around here a little bit, but it's pretty much a constant value. Okay. But these are the settings that we have to go through to get the oscilloscope set for capturing a transient response like this. Okay. All right, so I'm just going to show you here why we don't press auto set. If I come along over here and I press auto set, okay, now I've just got crazy noise on here. My voltages are way down here to 20 millivolts. And if I now try to initiate the system, there's nothing on the screen because it's way up here above the scope, so I've got no data at all. All right. So again, let me walk through this on setting it up then. So I'm going to go to channel 1, I'm just going to make sure it's still DC coupling and a 1x probe. Sometimes it'll even change that on you on auto set. I don't know why. So we just want to verify both our channels are DC coupling 1x probe, because that's the probe I'm using. And then I can adjust my voltages here. So I'm going to adjust the voltage to be 1 volt per division. Okay, for both of those. And then my time scale is on 1 microsecond. You see how all that noise that's buzzing around there? That's noise that it's picking up because it's 1 microsecond. All right, so that means each division is 1 microsecond. So what we're doing is we're just seeing noise in the system from wherever the noise is coming from, and we're not really concerned about that. Okay, if we were, we might want to try to do something to reduce the noise. But what I want to do is I want to change my time, and I'm going to sit here and crank it. Now you see how long, now you can watch it going across the screen now, because now I'm up to half millisecond. But also notice that the trigger point is in the center. Okay, so I'm going to have to shift this. Oops, I was shifting the horizontal position. And I think what I need to do is press single to get into single mode. And now I can see the trigger. So it was just the auto set uses a auto trigger generation, and usually, so just noise is enough to trigger that. Okay, so also it put my ground way up here at the top. Okay, I want my grounds down here so I can capture as much of the response as possible. Okay, so you know, for this system here, I'm going to start from 0 and go up to my step is 5 volts. So I'm going to be stepping up to 5 volts. So that's going to be 1, 2, 3, 4, 5 volts. So that should fit on the screen. Okay. So when I do that, so again, I'm going to put my trigger over here. And I've got both my grounds set down here at the bottom. And I set this trigger level. You see it reset the trigger level to 0, which is why it was triggering on just noise. And so I'm going to set the trigger up here, somewhere up above the noise level. Okay. Don't want to necessarily be too high because I want to make sure I capture the change when it changes from 0 to 5 volts. Or whatever, but I need to set that. So I set this on single. It says it's ready. So now if I energize the system, it will actually go through and capture this waveform. So it says triggered there, but it takes 10 seconds. Now I changed my control settings so it didn't bounce around quite so much here. So this is now the yellow, what we're looking here at the yellow is my input into the system. But if you look at the block diagram, remember the block diagram, the set point is set to 5. So we have the set point here is set to 5, but it's going to the control system, which is my PLC basically, and outputting that voltage. All right, but it's actually right now I'm doing closed loop control. So when I do closed loop control, it's the set point is set to 5, but it's comparing it to the previous value, and it's doing proportional control and adding gain in here and amplifying it. And so when we do that, we're actually getting some overshoot. Okay, so that's what we're seeing there. But the yellow is what we're feeding the system. So the yellow is what we're feeding the system. Now remember that my RLC circuit here actually has a two resistors, a 50 ohm and a 1K ohm resistor on here. This is the setting for the 50 ohm with a gain of 1 into the system. So I have a gain of 1. If I flip this to the 1K, so I flipped the switch, you didn't see me do that, but I flipped the switch here. and I'm going to hit my scope. So I'm going to go to single mode now, and I'm going to energize the system. I should have, that's the decaying signal there. We don't want to see that. So I'm going to hit single again and re-trigger it. So it's ready. Now I'm going to energize the system and wait 10 seconds here. And now you can see, because I have so much more resistance, there's no oscillation here. So the signal just starts, and the blue is my capacitor, and I'm simply charging up my capacitor. All right. Now, what you're seeing here, this yellow is the control signal. The control signal is maxing out, okay, at 5 volts. 1, 2, 3, 4, 5 volts. Okay, because that's the maximum error. Okay, because my set point is 5 volts. And so the error is 5 volts and my gain is 1. So I'm multiplying it times 1. So I have a gain of 1. Now I'm going to increase my gain to 2. I'm going to run the same system but with a gain of 2. Okay. And so it should actually go up to 10 volts. Okay. So I'm going to hit single again to initialize this. And then I'm going to energize the system but with a gain of 2. And it's triggered and it's captured it. And you see how much faster the blue came up because I charged it faster. But look what happened to my yellow. My yellow is off the scope. If I change it down to 2 volts per division, so we see that it actually capped at 10 volts. Why did it cap at 10 volts? Well, because the PLC, the max the PLC system can output is only 10 volts. So it even though my error was, I went from 0 to my input, which was 5 volts. My set point is 5 volts. So my error was 5. And so times 2 gives me 10. So it actually capped out here at 10 because that was my largest error. So I'm putting out 10 volts. The control is 10 volts for a little while. And then as it starts getting close, the control backs off. But you notice there's no overshoot or bouncing around. Okay. Now, if I hit single here again, but I switched it back to the 50 ohms. So now I'm back to a 50 ohm resistor, and I do this with a gain. And what you're going to see is lots and lots of oscillations here. Okay. Now, again, the yellow is my control. And so what it's doing is it's pushing the system, but now after the system overshoots, the control goes, see how the yellow is below the blue? So what happens is it starts pushing, it sees that, hey, the system has now gone over the 5, because it should be going up to 5, and it sees that it's actually over 5, so the control system starts pushing it down, okay? And it starts pushing it down and is responding to these changes. Okay, so the yellow is the control system, the blue is the response.